Our next speaker is William Vaughan from Brown University. He's a grad student, I believe, working with Jim Head. And he will be talking to us about the impact melt differentiation in the South Pole Aitken Basin. And that does not look like William.
No, it does not. It looks like his advisor, Jim Head. Sorry about that. Will is under the weather at the moment, so I'm happy to present the work that he's been doing, and I also refer you to an Icarus paper that came out earlier this year on both the Oriental Basin and the...
We're not seeing the arrows on the presentation to advance it.
Can you...
Oh, there you go.
Okay. So I'll just say next slide. Is that okay?
Yeah, that works.
Okay. So as everyone knows, in the early solar system history, a huge number of impacts created the planets, and also giant impacts associated with that frequency distribution of impactors caused massive melting, like the lunar magma ocean, et cetera. And ultimately, that created igneous differentiation, such as the anorthositic crust on the moon. Next, please. So if we take a look at individual impacts, we can see, in fact, that giant impacts can also occur in terms of multi-ring basins and other things like that, and actually cause pretty massive melting. And if the impact excavates down into the mantle, of course, it's really interesting what the combined melt will be and what happens to that melt. Next, please. Now, what we're going to talk about today is kind of an introduction to the problem of the felspathic floor of the South Pole Aitken Basin, well known to everyone, and one possible solution, which is, in fact, impact melt differentiation. So there's spectroscopic and geophysical constraints on the South Pole Aitken stratigraphy, and in fact, we can use that to think about how to consider this as a possibility. So modeling impact melt differentiation in SPA, which we do on the basis of these data, and then think a little bit about the implications of impact melt differentiation in SPA for both geophysics and geochemistry, as well as, indeed, sample return. Next, please. If we think about this, it's well known, of course, from studies that go way back into the last millennium, that there are large volumes of impact melt in the large impact basins. Oriental is about 930 kilometers in diameter. It's not the biggest basin on the moon, but clearly it's exposed, and we can see huge volumes of impact melt, which have been mapped by many workers. And these things, in fact, melt deeply into the moon's mafic interior on the basis of most of the modeling we've heard about from Gareth Collins, Ross Potter, and all their colleagues. They produce mafic impact melt, and the bigger the impact, the more mafic the impact melt, because they're excavating down potentially into the mantle. So it stands to reason that very large lunar basins, such as the South Pole Aitken Basin, probably a factor of 2 or more larger than Oriental, would melt really deeply into the mantle, and should host extensive mafic deposits of impact melt in their interiors. Next, please. If we take a look, though, the floor of South Pole Aitken Basin, which ought to have excavated at least 200 kilometers into the moon and melted even deeper, deeper than the excavation, is noritic, not mantle olivine pyroxenite. So why is the floor of SPA, which is probably primary, so felspathic? And so it could be due to a couple of things. Maybe anomalously shallow excavation by oblique impact. Pete Schultz has suggested that. Maybe non-proportional scaling. Warwick and Phillips has suggested that in a 1999 paper. Another possibility is impact melt differentiation, as we're alluding to here. This would be igneous differentiation of a thick SPA melt sheet, essentially by crystal settling, and this would concentrate felspathic components to form a noritic floor overlying ultramafic cumulates. Now, in a paper in 1998, an abstract, Don Morrison, showed, in fact, that very presciently that this could be the case, and proposed that this was a major factor there. So the question is, does IMD really explain, that is, impact melt differentiation, really explain the SPA stratigraphy? We'll test this hypothesis. Next, please. If we take a look, the surface of SPA is norite. This has been shown by a number of workers. And the question is, what lithologies are present at depth? Dan Moriarty has done a lot of work on this, and in fact has presented several discussions on this. And so there's a lot of information here that Dan and colleagues have put together that let us get at this issue and test this idea. Complex craters exhume subsurface material for spectroscopic inspection. You can see the list of the craters here and their locations. So we compiled data on these complex craters with previously characterized central peaks, the craters at the left. Next, please. If you take a look at these, you can see from the data, we calculate the depth from which the central peak material is excavated or derived by using a formula from Santala and Grieve, and then essentially central peak lithologies, as I mentioned before, are determined spectroscopically. Tompkins and Peters, Nakamura, Yamamoto, Dan, many others have taken a look at this, and we assume a radial symmetry of the subsurface strata for simplification, if you will. If you take a look at these data, olivine-bearing lithologies shown in green here are present only at depth, maybe is of the order of 40 kilometers as shown in the synthesis diagram in the SPA subsurface, and this would be in Zeeman and in Schrodinger. So orthopyroxene-bearing lithologies overlie the olivine-bearing lithologies, and the proportion of orthopyroxene decreases with decreasing depth. But the question is, are the deep peaks norite or pyroxenite? There's differences of opinions about this. Next slide, please. So if we take a look at some of these things, we can use the VNIR spectroscopy, but it poorly constrains the depth at which the noritic materials transition to the pyroxenite. And this depth is actually well constrained by gravity data. It's simply the crustal thickness. So New Grail-derived crustal thickness models, recently published in Science by Wazurik et al. In 2013, indicate that there's about a crustal thickness of about 12.5 kilometers of norite. Next, please. Now, if we take a look at this, the primary stratigraphy of SPA, according to spectroscopic and geophysical constraints, then, is about 12.5 kilometers of norite, overlying orthopyroxene-rich and olivine-rich lithologies. Next, please. Now, modeling impact melt differentiation is different from magma ocean modeling. In this case, we know relatively little about the cumulate layer composition, but a lot more about layer thickness and position. So the strategy is to use simple phase equilibria combined with mass balance of components between initial melt volume and the final cumulate layers. So the crust-mantle proportion of melted material controls the melt composition. The question is there enough crustal Al2O3 in mantle-dominated SPA impact melt to make 12.5 kilometers of norite? Next, please. So when we take a look at this, the SPA melt sheet is indeed, like is shown here, an orthopyroxene and olivine-rich mixture of plage, OPX, and olivine. Ilmenites minor, probably low titanium Mare basalts. Crystallization sequence would be olivine, orthopyroxene, plagioclase, OPX. And the stratigraphic sequence, assuming that all crystals sink, would be dunite and pyroxenite below norite. So the mass balance for the layer proportions are shown here. And indeed, if you follow this very simple but logic using the spectral data as well as spectroscopy data as well as the gravity data, in fact, the model stratigraphy fits about 12.5 kilometers of norite. Next, please. Now, there's some implications of this if the logic and our sequence of thinking here is true. That is that from a geophysical point of view, the 12.5 kilometer crustal thickness of the SPA interior is not the thickness of primary crust, which may well be, in fact, 0, but of a noritic impact melt differentiate. So it's low density. It appears more like lower crust in the gravity data, but in fact, it's the upper part in this model of the impact melt sequence. So non-zero thicknesses do not mean that basin-forming impacts didn't excavate the local primary crust. So you can have what looks like primary crust, but the basin may have excavated much deeper than that. Geochemical implications would be that the noritic floor does not need to be lower crust. It could be an impact melt differentiate, and this explains, of course, potentially the thorium concentrations on the floor as well. And in terms of sample return, the really good news here, if all this is true, which we're hypothesizing that it fits pretty well, is that the SPA impact melts have the potential to date the SPA forming impact and test the lunar cataclysm hypotheses. So if the whole noritic floor is an impact melt differentiate, you can literally land a mission like Moonrise almost anywhere and be pretty confident that you're going to be able to date impact melt, which would in fact give you a date of the basin. So this is really interesting from the point of view of a lot of debates we've had and suggests that impact melt in the interior of these basins may be much more widespread than one might think, and in fact just based on simple interpretations of the data, and in fact that we might be able to use this in the future to strategize and think up ways in which we can date not only the South Pole Aitken Basin, and you heard from Bill Botke and other colleagues how important that is to date in the overall chronology, but also the other major basins and really see if they're focused together in single peaks, so to speak. Next, please. So if we take a look at this then and think about a few conclusions, impact melt differentiation probably took place on the Moon in terms of these huge basins. We see evidence from that geologically in the deposits that are seen left in the places like Oriental Basin, et cetera, and evidence for significant amounts over 10 to 15 kilometers in that basin alone. You can refer to Will's paper in Icarus. So the interior stratigraphy of SPA is consistent with that of a differentiated melt sheet. So this could be an interpretation for the geological and mineralogical and geophysical relations we see there. Impact melt differentiation helps to clarify some of the unusual aspects of the geochemistry and geophysics of SPA. And the interesting thing is that if all of this is true and survives further tests and analyses, then the same probably goes for largest lunar basins like Nectaris, Oriental, Serenitatis, and Imbrium. And these ought to contain differentiated impact melt sheets too. And this is really important. We can test this looking at spectra and do modeling of impact melt differentiation there. But even more importantly, in terms of our quest to understand the chronology of the Moon, this means that if this is true, that we could go there and stand a good chance of dating these basins, even though they might be really old, because in fact a significant part of their interior deposits would be of impact melt origin. Thank you very much.
Thanks so much, Jim. And it must be nice having a proxy of Jim Head to give your talk for you if you're feeling under the weather. So thanks very much.
It's 100 degrees here, so.
Yeah, it sounds like it. Catherine asks, can large basins on Earth be dated in this manner, i.e. Sudbury crater?
Let's see, I think if you've managed not to overprint these large basins early on, and have impact melts like one does in Manicouagan and other basins like that, I think the answer is yes. The problem really is that there's a significant amount of overprinting that occurs due to subsequent metamorphism, et cetera. But in principle, it should not be a problem.
Great. Simone says, Jim, very nice work. What is the time scale for solidification of this huge melt sheet?
Simone, this is a question we talked about in my office just a couple of weeks ago, and the answer hasn't changed very much. I think the simple thing to do is we're talking of the order of hundreds of thousands of years, generally to maybe a few, several million, but not so much to make a significant confusion related to multiple ages, et cetera. So I think it would be something of the order of less than a few million years, which would be a really nice age to be able to get for something like SPA.
Fantastic. Thank you so much, Jim. I think we're going to go ahead and move on to our next talk. Give William our best. Hope he feels better.